In this lecture, we shall be talking about the RMS and average values and how to evaluate them. But before that, there are a few characteristics that were left out that we needed to learn. One of which was phase. So we learned the expression of representation of a sinusoid wave as AT equal to m sine omega t plus 5. So here we see that there is a term that had been included which was not present in our previous lecture, and this term in fact is the term called as the phase. And this is the characteristic of the sine wave which decides the shift in the time axis or the omega t axis or the x axis. So for example, if we talk about the three waves which are shown here, so one of which is at am sine omega t, the first case, this one. So if we consider this is the first case, and let's say this is the second case, and this is the third case. So in the first case, we have the expression given as at equal to am sine omega t, and the waveform is given as shown here. So we have the maximum value of this waveform as am, and the normal representation that we learned in the previous lecture. So it represents a sine wave, and in this case, since we have this phi is taken as 0 in this first case. So which means that the waveform will start from time t equal to 0, and notice that we have written this as omega t. So ideally this axis should also have been omega t instead of only t. Let us correct this. This should be omega t. And thus this will be omega t equal to 0. And the corrections will apply in the second and third figures as well. So suppose that in the second case we have a phase angle which is positively shifted. So this waveform will be having expression as at equal to am sine omega t plus phi, which means that it will be having a positive phase or a leading phase. For the time being, let us only talk about positive and negative phases, not lag and lead, because lag and lead are something that will be uh, talked about when we try to compare one waveform with the other. So this particular waveform has a positive phase, which means that the maximum value of this waveform will be shifted slightly towards left, or shifted by an angle of phi towards left. Likewise, a negative phase waveform has its peak shifted by an angle phi towards right. So this shift by a phi represents, on the right side, represents a negative phase, and the expression is given as at equal to am sine omega t minus phi. Now for example, if suppose that we have the waveform, we compare the voltage and current waveforms. So shown here is the voltage waveform in blue and current waveform in red. So if you look into these two waveforms, so we have their the time of start same, their peak appears at the same moment, at the same time, and the waveform shapes almost appear at the same time, and thus we say that these two waveforms are in phase. So the first case corresponds to the in phase situation, where the current and voltages are in phase. Well, if you look into the second figure, we have the peak of this current that appears later to the peak of the voltage, which means that the current is lagging the voltage. So if you try to write the expression for this case, let us write the expression. So in this case we have v, let us assume this is vm, so it's already given there. So we have vm, the maximum value, vm sine omega t. If this is the expression for voltage waveform for the blue curve, then the current waveform would be written as Im sine omega t for the red waveform. Now in the second figure, if suppose that voltage is given as, let's say, V, and of course they both are, in this case, voltage and I, small voltage and small v and small I, both are function of time, omega t. Likewise, here we have v function of omega t, and let us assume that this is Vm sine omega t. So the current would be written as I equal to Im sine omega t minus phi. I equal to Im sine omega t minus phi. And we have taken the phase as negative because we learned in the third case here that the phase is going to be negative if the peak is going to shift by the phi amount towards right. So since we see that the peak of the current is shifted towards right compared to the peak of voltage, and hence we say that the phase of current waveform lags the voltage and will be having a negative phase as written here. So this particular example is the case of current lagging voltage by 5 degrees. So this example shows the current to be lagging, or in other words, we can say that voltage leads the current by an angle of 5 degrees. So this gives a rise to the concept of lead and lag, and we'll talk about this later in detail, that what are the phase that are leading and lagging. Now we define the term instantaneous value. So instantaneous value are the value of alternating quantity. So alternating means that what we had been talking about. Sine wave, for example, is an alternating quantity. So the value of alternating quantity, that could be current or voltage, at a given instant of time is called the instantaneous value. For example, suppose that we are given a waveform shown in red here. So the values like I1, I2, I3, which are highlighted in yellow, are the instantaneous value corresponding to, let's say, time t1, and say let us say this is time t1, and say the next time, this particular time corresponds to time t2, and this is, let's say, time t3, and so on. So the values of current at time t1, which is I1, then again at the next time t2, which is I2, and time t3 is I3. So these values are instantaneous values, and this can be written in they can be tabulated. For example, let's say we talk about the time or the instant, let's say t, and we write the values of current in amperes in that instant. So let's say for the time t1, let's say for example we have the value of current as 2 amperes. For time t2, we have current as 3 ampere. For time t3, we have, let's say, 4 ampere, and or let's say 5 ampere. Of course, this is a sinusoid wave, so this should be the gap should reduce. And okay, let's say this is 3.5 amperes, and again and so on. We will be having different values of current at different instants of time. So these current values are nothing but the instantaneous current values of the given waveform. And likewise, we talk about the average or mean value. So the average value of an alternating quantity over a given interval is the sum of all the instantaneous values in this interval divided by the number of values taken over this interval. So what does that mean? Suppose that we are given a curve as shown here. So if you see that in this particular curve, this also represents sine wave, but the definition applies to any curve. So it may be a curve that looks something like this. Let's say this is the curve, and we may be talking about computing average between the points A and B. Let's say this is T, this is amplitude, small a. We have taken a here, so we'll be calling this as small p. So let's say we have a curve. It could be fx, f versus f of t, if this is t. So f of t or p of t, and likewise we have a curve here. So let's say we are interested to compute the average value between point A, this, and this. So in order to compute the average value, it says that we will have to sum all the instantaneous values which lies between A and B. Now if you look into this curve, this is continuous time curve. So the values are continuously varying rather than discrete. But just to explain things, so let's say that we have this particular uh, instant. At this instant we have certain value. Then again in the second case we have at t2 certain value, at t3 this is the value. So in order to compute the average of all this, what we do is, let's say this represents current. So we have the values of current. Let's say this is I1, second is I2, third is I3, and so on. And let's say we have in total, let's say this is I100. So this is an arbitrary value 100. It could be 50 values, it could be more. So we just for the sake of explaining things, I've taken 100. Books have taken this as n. So in order to find the average value of this waveform, what we do is we sum all the values at different instant lying between A and B, and divide them by the total number of values. So in this case we have 100 values, so we'll be dividing this by 100. And let's say if we had this, if we try to generalize this and we take this as n, so this can be written as I1 plus I2 plus I3 up to In, and this will be divided by n. And likewise in this particular case the same definition can be applied. You will have to count the number of instantaneous value that lie between A and B, and you will have to sum all those instantaneous value and then divide by the number of such values. So this particular definition, this applies only for the discrete values or the instantaneous value, but in fact what we have a continuous time curve, and thus instead of applying this definition, if you remember the calculus that you learned, and we say that there are infinite number of such instantaneous values lying between A and B because the curve is continuous. So instead of writing the average value in terms in this form of expression, we write this in the form of the integration, and that is, you will have to integrate this curve from A to B. So if you talk about this curve, the average value can be found by taking integration from A to B, and P dt divided by B minus A, which is the length of the curve. So in fact this particular thing represents the area under this particular curve. If you talk about this curve, the area under this curve divided by its length, or the time duration for which the average is being calculated or we are interested in. So this is the formula for computing the average value between the duration A and B. And likewise we can write for this case, so let's say this is a curve I, and the x-axis represents t. So this can be written as I dt divided by B minus A, and the integration will be taken from A to B. So the limits are from A to B because this is the range in which we are interested to compute the average of the curve. So let us consider this with an example. Let's say we are given a curve, sine wave of current versus t or omega t, then accordingly you'll be taking the values or the limits. So let's for the time being take this as t, and we'll talk in terms of omega t later. So let's say we have a sine wave, and this is the maximum value Im, and then the minimum value is minus Im. Now in order to compute the average value, let's say for the duration A to B, so we are interested to compute the average value between the durations A and B, and we learned that the average value can be computed by the expression given as integration from limit A to B and I dt divided by B minus A. And since for this sine wave we have the value of I as Im sine t dt divided by B minus A. And I repeat this because we are taking the x-axis as t and not omega t, and that is why we have written this as sine t and not sine omega t. Had this axis been omega t, so in the case when we have omega t here, then we would have an omega t. In place of t we would be writing this as omega t, and in place of dt we would be writing as d omega t. Now let us try to understand this by a simple example. Let's say we are interested to compute the average value, and so suppose that we are interested to find the average value of an AC current, and that AC current is given. So find the average value of an AC current, which is given as, let's say, I equal to 100 sine. So you can write omega t or t. So let's take this as, let's say, t. So which means that you will be drawing the waveform of I with respect to t and not omega t. So by definition, average value is given as integration from, and since we are not given the limit, or let's say we in the question it's given that you are required to find the average value in the period in the time 0 to pi. So let us say that it had been defined in the question that the average value of the current is to be computed between the limits 0 and pi. So we got the limits as 0 and pi, and I dt divided by pi minus 0. So we obtain this expression by definition, and when we place the values as 0 to pi, I is given as 100 sine t dt divided by pi. So this can further be written as, if we take this 100 out, so this is 100 divided by pi, and the integration of sine is minus cos. This is minus cos of t 0 to pi. And if we further simplify this, so you can use, no need to use calculator, so you have cos of pi as minus 1, minus cos of 0 is again minus 1, so this gets minus 2. So we have minus 2 multiplied by 100 divided by cos of pi. We take this minus out, so we are left with cos of t limit from 0 to pi. So cos of pi is minus 1 minus cos of 0 is minus 1, so this gets minus 2 and minus minus gets plus. So what we get is 200 divided by pi. So this is the average value of the current, which is given by the expression I equal to 100 sine t. Now if we talk about the next concept, that is about the RMS, how to compute the RMS value or the root mean square value of the alternating quantities. So the RMS value, or also called as effective value of the alternating quantity, which can be current or voltage, is the equivalent DC value of those current and voltage, which when applied to a given resistor for a certain time produces same heat as produced by the alternating quantity current or voltage when applied to the same resistor for the same time. So what does this mean? This means that if suppose that we are required to compute the RMS value of a given AC source which is connected across a resistor R. So let's say the voltage or the current value of this source is small I, which represents the AC quantity of this particular source, and what we say is the RMS value of this alternating quantity, this current, is what is the DC value, and we represent this by IRMS, which when connected across the same resistor R. So what we are trying to do is we have this alternating quantity which is connected to this particular resistor, and if this quantity is allowed to pass through this resistor, which dissipates the amount of heat, let's say the power which is dissipated by the resistor is I square R, while the energy that had been dissipated by this resistor is I square R T, let's say T naught. So we say that the DC value that is going to dissipate this amount of energy when connected across the same resistor for the same time, is the RMS of this particular AC current, which means that this particular current is going to be RMS of this alternating quantity when it is going to dissipate the same amount of energy. So energy dissipated in the circuit, which is I RMS, and it's the DC value R T naught. So this resistor is same, the time is same. So the condition for the DC value to be the RMS of the AC source is that this amount of energy should be equal to the energy which is dissipated by the alternating current. So if this energy, let's say this is energy AC and this is energy DC. So if these energy are going to be equal, so energy AC is equal to energy DC, then we say that the DC value I RMS is the RMS value of the alternating current I. So I have priorly written this as RMS, and this should ideally not be written priorly. We should have written this as capital I, and when we come with the conclusion that energy AC is equal to energy DC, then we say that I is the RMS of small I. So this can easily be proved. So we can obtain the expression for the RMS value. So let us say that we have, let's say we have an AC source and that portrays a sinusoidal quantity as shown here. Let's write this in terms of t instead of omega t, just to make things simpler. And we'll be talking in terms of current. So we are after obtaining the expression for RMS value of current, this will be applicable to all other sinusoidal alternating quantities. And let's say the energy that had been dissipated by the current source between a duration a and b. So we'll talk in terms of the instantaneous values. Let's say we have in this particular current values, let's say we have the instance at t1 we have current I1, at t2 we had current I2, at instant t3 we have current I3, and so on. And if we compute the power that had been dissipated in this particular uh, by this particular current, so the power dissipated by this will be I1 square into the resistor R1. So we are going to supply, or we have a source, AC source, which is connected across a resistor R. So the power dissipated in this resistor is I1 square R, and the power dissipated at this particular instant is I2 square R. At this instant it's I3 square R, and so on. And let's say we talked this corresponds to a duration of, let's say, time t. So we were interested for a time period of capital T. So that could be the time period of the sinusoid cycle, or any other time. It could be half cycle, it could be full cycle, or a partial cycle, a part of this particular cycle. So that could be any time. And for the we are assuming that for this particular time we have number of readings as number of instantaneous values varying from I1 to IN. So let's say the last value that we obtain is IN, and the power dissipated by this would be IN square R. Now we say that there is a DC value of this alternating current, which would be called as RMS if it is connected across the same resistor and it dissipates the same amount of energy within that particular time for which the AC quantity is giving supply to the resistor R. So that is capital T. So it means that if we are going to connect this source, the DC source, to this resistor, and the energy it dissipates is I square R. I square R is the power, and let's say for time duration T, because we have taken the duration capital T for AC, and the same duration is being taken for the power which is dissipated in resistor R. So the total energy which is dissipated the duration and during the time capital T. And by definition, capital I can only be qualified as the, or can only be called as RMS value of this AC if it satisfies the condition that I1 square R. So let us compute the energy that we dissipate in case of the alternating or AC values. So if these are the power dissipated at different moments, at different instants, then the total energy that would have been dissipated is I1 square R, I2 square R plus I3 square. So instead of talking in terms of power, let's say the energy dissipated at every instant is, so if there are n number of readings within duration t, so each reading occupies a time. So how much time would this the first reading take? It's t divided by n. If there are I1, I2, I3 up till IN number of instantaneous values within duration capital T, this means that each of these current will be occupying or taking a time capital T by n, which means that the energy which is dissipated in the first reading would be I1 square R T by n. This is the energy dissipated by the first instantaneous value. The second instantaneous value dissipates energy I2 square R T by n. then I3 square RT by N plus and so on up till IN square RT divided by N. So this is the total amount of energy which is dissipated by the alternating quantity or the AC within a duration of capital T. And of course this is a sort of assumption because we are taking the instantaneous value from the continuous representation of the waveform, but this is enough to come up with the picture or come up with the conclusion of how the RMS of the AC quantity can be computed. So we say that the value of capital I in case of DC source is going to be the RMS of the AC when the energy which is being dissipated by the DC within the same time capital T when connected across the same resistor is equal to the energy which is dissipated by the AC source. So this should be equal to capital I square RT. So if this is going to be, this particular expression is going to hold, then we say that this I is the RMS of the AC quantity I, small I. So now we can further generalize. We have written this expression I square RT by N. So let's first of all take the expression of RT as common. So let's rewrite this. So this can be written as R capital T taken outside, and we have I1 square plus I2 square plus and so on up till IN square divided by capital N, which is equal to I square RT. And again, now if we further look into, first of all, we cancel out these two terms, RT and RT, they cancel out. So what we are left with is I square I square equal to, so this is the DC value, and again we can write this as RMS. So in short, you can write this as IRMS. You can write IRMS here as well, or you can say by definition this is going to be equal to the AC energy. Then we have IRMS, this I as IRMS. So IRMS can further be written as under root I1 square plus I2 square up till IN square divided by N. And if we further generalize this, so since we had assumed we have taken instantaneous value in the continuous curve, and we come up with an expression having instantaneous values. But for the continuous representation, for the continuous curve, we are not going to have finite number of instantaneous values, rather the values will be infinite. So now what we do is we replace this by the integration term as we did in case of the average value. So what we do is we have the integration and then the limit. Let's say the limit is from A to B or 0 to capital T. If we start from 0 and the total time for which we are interested to compute the RMS value is capital T, and then we have the continuous values given by small I. So we have these values I1 square plus I2 square. So the addition is being replaced by the integral term. So this will be I square and then dt. So this is a simple calculus that you already had been studying, that how you replace these summations by an integral if the curve is shifted from discrete to continuous time. So these are the expressions that hold for discrete time curve, while this is the expression that holds for continuous time domain curve. And again, this will be divided by, since we talked about n small n as the number of readings that were taken in the interval of capital T, and thus we'll be replacing this n by capital T. So this is the required expression for the RMS value. So IRMS is given by 1 upon capital T integration from 0 to capital T I square dt. Now notice that we have the interval in this case taken from 0 to capital T. If we were interested to compute the RMS value between interval A and B, let's say we are interested to compute in this interval A and B. In that case, what we write the expression of RMS, we take the limits from A to B like this, and this T will be replaced by 1 upon B minus A, which is the length of the curve. So I guess this is clear to all. And in the similar manner, so we have obtained the RMS value of current as IRMS. So this RMS value of any alternating quantity for a sinusoid, for any other expression, for example, let's say voltage. So if suppose we are interested to find the voltage value, the RMS value of voltage, then VRMS will also be given by the same expression, that is under root limit 0 to A to B, or it could be 0 if we start from the 0 interval, and then we have small v square dt divided by b minus a, where small v or small I that we have taken here are the instantaneous values. So let us try to do and try to understand how to compute the RMS value using an example. Or let us first compute the average and RMS values of sine waves, full wave and half waves, and other waveforms as well. So we start with the average and RMS value. Of sinusoidal current or voltage. So we already have seen that the current value is given by small I as Im sine omega t, and we are interested to find the average as well as the RMS value for this particular current, and we will be dividing this into two parts. One is for the full cycle, since if you draw the waveform, I versus omega t. So there are two possibilities. One is that you compute the average and RMS value for the full cycle from this to this. And the other possibility is that you compute for this for a different duration, for example, a half cycle from this duration, from this point to this point. So this is half cycle. So we'll be computing the average and RMS value for the first full cycle first and the half cycle next. So let's talk about the full cycle. So for full cycle we have from 0 to 2 pi. So by definition the average value is given as summation from 0 to 2 pi I d omega t. Now we are going to take this as omega t and not t, divided by the length of this curve is 2 pi minus 0, which is 2 pi, and 0 to 2 pi. So small I is, if you take this as the maximum value is Im, so let's say the maximum value is Im, So small I can be written as Im sine omega t d omega t divided by 2 pi. We take Im, which is always constant outside, and then we are left with 0 to 2 pi limit sine omega t d omega t. So this can be further written as Im divided by 2 pi. So this is minus cos of omega t. If you integrate sine omega t, you get minus cos of omega t from 0 to 2 pi. Now if you take this minus sign outside, so this is minus Im by 2 pi cos omega t from limit 0 to 2 pi. Now if we are going to substitute the limits, so cos of 2 pi is 1 minus cos of 0 is 1. So 1 minus 1 is 0, which means that the average value for full cycle of the current comes out to be equal to 0. And this is of course clear from the figure as well. So if you see that we have positive half cycle here and negative half cycle here, and if you talk in terms of instantaneous value, so the number of values that we get in the positive cycle will be same but with negative sign in the negative half cycle. So in the negative halves, the average which will be giving you negative and will be equal to the average that you're going to get in the positive half cycle, and thus all the positive values added with the negative values will give you 0, and this is also proved from the definition of the average value. Now if we talk about the RMS value of the full cycle, so this was the average value. Now we talk about the RMS values. So by definition, the RMS is given by A to B. In this case, this is 0 to pi, 0 to 2 pi for full cycle, and 1 upon capital T. Capital T here is 2 pi, or B minus A, which is 2 pi. I square d omega t. And RMS value can further be written as 1 upon 2 pi, 0 to 2 pi, Im sine omega t square d omega t. So we take Im out, so we are left with Im divided by root 2 pi. Then inside this we have, so we have sine omega t square. So in order to compute the integration of this term, we'll first convert them into the term 1 minus cos 2 omega t divided by 2 and d omega t, which can further be simplified, and this can be written as Im divided by root 2 pi inside under root we have. So now we are going to compute the integration of this one, since we are writing this in terms of d omega t. So this can be written as omega t minus sine 2 omega t. So let's take this 2 outside as well. So 2 sine 2 omega t divided by 2. So this is a different 2 from this one. And then we have limits 0 to, we were computing this for full cycle. So this is 2 pi, 0 to 2 pi. Now if you are going to substitute the values, so if you are going to substitute in place of omega t as 2 pi, so what we get is, so let me write this here. So we have I RMS. We're talking about RMS values for full cycle. This is Im divided by 2 root 2 pi under root 2 pi minus sine 2 into 2 pi is sine of 4 pi, which is 0. So this can be written as 0 minus omega t is 0. When 0 is substituted here, we get 0. And again, if we substitute in place of omega t 0, we get this as sine of 0, which is again 0, plus of 0. So what we are left with is Im. Okay, I did commit a mistake here. So this is not 2, rather root 2. So since we were having this 2 inside the under root, so this is root 2. So Im divided by root 2 into root 2 pi, and what we are left with is root 2 pi in the numerator, and this cancels out. So the final expression that we are left with for the RMS of full cycle is Im by root 2. Likewise, we can compute the average and RMS value for half cycles, and we'll see that what is the difference that comes in the half cycle compared to the full cycle. So let us redraw the waveforms and rub this all. The B part is for half cycle. So we shall only be focusing on the half part of the waveform of the current, so which means that we'll be talking in the range of 0 to pi only and not 2 pi. So for this half cycle, if we compute the average value, so average value of current is what is given by definition we have from 0 to pi I d omega t divided by length of curve is pi minus 0. So 0 to pi I m sine, where I m is the maximum value of the curve, sine omega t d omega t divided by pi. I m by pi comes outside, and what we are left with is cos minus cos omega t, and the limit is taken from 0 to pi. So now if we take this minus outside, Im by pi, and cos of pi is minus 1 minus cos of 0 is 1. So the average value for half cycle comes out to be 2 by pi Im. So this is the average value for half sine wave. Now you will have to notice here that this is different from the average value computed for full wave. So for full wave we were having the average as 0, while for half we have this average value as 2 by pi Im, and 2 by pi lies somewhere between 0 and 1, which means that the average value would be lying somewhere below Im. So we can say, if we indicate this as I average, so I average would be somewhere below Im. And likewise, if we are interested to compute the RMS value, so this is given by IRMS, which is RMS value, which is from 0 to pi. So the definition changes. For RMS value, we have the definition as root 1 upon pi minus 0. Then we have integral 0 to pi I square d omega t, and this is equal to 1 upon pi 0 to pi I m sine omega t d omega t. So this can further be written as under root 1 upon pi, and of course I forgot the square terms. So I m square 0 to pi sine omega t square d omega t. So using the same things that we did in the previous full cycle mathematics, so I'll be writing this directly. So this can be written as, if we take Im outside, so we are left with it is Im by under root pi under root. So in place of sine omega t in the previous case, we wrote as 1 minus cos 2 omega t divided by 2, and we took the integral of it. So what we got was omega t minus sine 2 omega t divided by 2, and the 2 root 2 was taken outside. So this can be written as Im by under root 2 pi. And then we substitute the limits 0 to pi. So if we further compute the RMS value and we substitute the limits here, what we are left with is Im by root 2 pi, then this gives us, in place of omega t we substitute pi minus sine 2 pi, this is 0, then we substitute 0 at omega t is minus 0, then 0 at this also gives plus 0. So now what we are left with, this gives us Im by root 2 pi into root pi, which is Im by root 2. So this is the required RMS value of the half wave. And if you remember in the previous part where we computed the RMS of full wave, the same expression was obtained, which means that the RMS of full sine wave and half sine wave are equal. Now in the next lecture we'll be talking about, or I'll be providing you the tutorial of computing the average and RMS value of different waveforms other than sine waves. So you'll have to do them yourself, and we'll talk about phasors in the next lecture.